Two-dimensional Fourier transforms, linking observations with theory. What are we going to do now? We're going to have a review of one-dimensional Fourier transforms. Well, many of you know all about one-dimensional Fourier transforms, and you don't need this review because you've already figured out the answers to the questions. But if you need the review, this is it. So just feel free to skip over this review. The first thing is a one-dimensional Fourier transform is really a complex valued matrix. An important part of it is anyway. We have two things that are varying. We have frequency. Oh, what did I do? Did I move the page? No, I didn't. We have frequency as a variable, and we have time as a variable. And so here's time running this way, and here's frequency running this way. So this thing is really, when you bring this e to the I omega t into a computer, it really becomes a matrix. And the matrix has a real part, and the matrix has an imaginary part. Now let's take a look inside of that matrix. When we look inside of that matrix, it could be a little confusing because there's a difference between physics and mathematics. I want you to ignore everything that's in blue because that's where the math and the physics don't quite agree. In physics, people like frequencies to go from minus pi to plus pi. By the way, this kind of frequency, when you're in omega, when I write omega delta t, it's dimensionless frequency, and that means it's really in sample time. You're counting time points. So frequency in physics goes from minus pi to plus pi. In mathematics, it goes from 0 to 2 pi. In computational mathematics, it goes from 0 to 2 pi. And that's just the story for frequency. Something similar happens for time. If we change from frequency to time, what's going on? And then the physics people like to go from time t equals 0. Things start to happen. Okay, so we got this issue that we don't... When you look in physics and math books, they have integrals that go from minus infinity to plus infinity. We don't have integrals. So I'm blotting off a bunch of stuff. And then I can explain e to the I omega t much more simply. Now, since the time axis is horizontally, let's look at the top row, and we'll see 0 frequency in the top row. See that? Just a black blob. And as we go further and further down, the frequencies get higher. And as you get way down to the bottom, every other point is alternating in polarity. This is called the Nyquist frequency. Shall I write that down? I'm not very good at writing here on this tablet. This frequency right here is called the Nyquist. The Nyquist frequency, the highest frequency you can have. You can see why I covered that up, because it's a higher frequency than the highest frequency you can have. Okay, something similar happens for the columns. This is getting a little bit messy in here. You can see there's a very low frequency here, something's nearly constant. And as we move this way, we're getting to higher and higher frequencies. Okay, so everything makes good sense in here to everyone, I assume. But when we get to the full matrix, it gets confusing because you have low frequencies on the first row, and the frequencies get higher, but finally they get to the Nyquist frequency where other points are alternating, and you get still higher, and they're starting to get low frequencies again. So a physicist would say, this stuff on the bottom here, a physicist would say these are like the negative frequencies. I'm just not accustomed to the switching between the pin. Negative, oh man. The negative frequencies are the bottom half. And when you get to the very bottom here, you're at the smallest negative frequency. And if we would continue this box down, what would we see? If the box was continued down, the very next one you see here would be wrapped right around to the top. Okay, so anyway, that's a point of confusion, that the boundaries here, what's kind of like infinity on the integrals is kind of like in the middle of this matrix. Okay, so if you want summations to be much like integrals, it's good to stay in the corners. where the frequencies don't get too high, the time lags don't get too high. Now let's look at this as a matrix multiplied. Let's call this an impulse function. This is an impulse, and it's an impulse function at time t equals 0. So I'm going to maybe depict this as a column vector, and I'm going to put the impulse right pretty close to the top here. So this thing has got zeros in everywhere. I'll put a couple of dots for some of those zeros. It's got zeros everywhere, but where this blurb is, this is a 1. So that means we have to do a matrix multiply, we have to take this column vector and we have to lay it on the top here, and there's a 1 in here. And then of course there's some zeros alongside of it. And now we grab a hold of this. I can't grab this thing and move it, but if I could grab this orange row vector and push it down through the matrix, multiplying, all it's going to do, the only thing it's going to see is what's inside this orange blob. And that orange blob is a cosine function. So what have we shown? We've shown that the Fourier transform of an impulse is a cosine function. It has an imaginary part, which is the sine function. Okay, so that's the basic idea there. So these are kind of issues that these sine functions and cosines, they continue outside the block. They just continue out here. And this one here, it just continues outside the block here. You have something in here, well, it continues outside the block there, and they're just periodic. And the physical domain, like in time and space, this is called wraparound. Physical means t and x. Time and space is the physical space. This is called wraparound. And in the frequency domain, omega and kx, it's called aliasing. And this can lead to a lot of confusion. It does. So the basic solution to these kinds of problems is, in the physical domain, you need plenty of zeros at the end for the infinite frequencies and the infinite times. And in the frequency domain, you need dense enough sampling on the time axis when you're recording your data. And that can be tough to do on space axis. And I didn't do it. I didn't sample these things as tightly as I should have or could have. And so you're going to be some problems because of that. Okay, what's going to come up next? Next, you're going to see the answers to the easy questions. But I hope you'll take some time off. I'm going to maybe even hide those answers until you've had time to work out the answers. Okay, see you later.